We had discussed Gauss's law in the last video. Now we are going to discuss, we'll represent it mathematically, general mathematical formula, representation of Gauss's law. Here is a closed surface in 3D. Suppose you have a charge plus Q here. Now let us take a surface here, small surface. Its area vector is ds. The electric field intensity at this point due to this charge is E. Angle between electric field intensity and area vector is theta. The flux over this surface, this small surface, d phi, will be, we learned earlier, it is E dot ds. Okay, the total flux over this entire surface will be the summation of d phi for our entire surface. You take small areas ds and find the d phi flux through that surface and add them up. That can be represented mathematically as surface integral, closed surface integral d phi. It is equal to surface integral vector E dot ds. This gives you the total flux over this Gaussian surface, whatever be its shape. By Gauss's law, we learned that this should be equal to surface integral E dot ds should be equal to Q, the charge enclosed by the surface, upon epsilon naught. This is the mathematical representation of Gauss's law of electrostatics. This actually is total flux phi E equal to this is the mathematical representation of Gauss's law. Now we'll prove Gauss's law. Actually, proof is not required in the board, but I'll just give a small proof, simple proof of Gauss's law. Here is a point charge plus Q. You can take an imaginary Gaussian surface around this point charge such that the point charge is lying at its center. Let the radius of this imaginary Gaussian surface be R. You take a small surface here. You know, at this point the electric field intensity E will be in this direction. Take a small surface here such that its area vector is also along E. What will be the flux over the surface? D phi, for that it is E dot ds. Angle between vector E and vector ds is 0. Therefore, this is going to be E ds cos 0. Cos 0 is 1. Therefore, E ds. What will be the total flux over this entire spherical Gaussian surface? It will be surface integral d phi, surface integral E ds. You know, the value of E will be, magnitude of E will be same at any point on this spherical surface, because all points on the spherical surface are equidistant, same distance r from the charge Q. Therefore, E being a constant, you can take it out with integral. For E surface integral ds. If you integrate ds for this entire surface, you add up all the ds for this entire surface, you will, what are you going to get? You are going to get 4 pi r squared, surface area of the sphere. But what is E? E is equal to 1 by 4 pi epsilon naught q upon r squared. So what do we get here? 1 upon 4 pi epsilon naught q upon r squared. This is the value of E into 4 pi r squared. 4 pi r squared. What cancels here? 4 pi, r squared gets cancelled. So what is left there? Q by epsilon naught. Therefore, we have proved Gauss's law. Phi is equal to Q by epsilon naught. We have proved Gauss's law. Now, we are going to discuss some of its applications. Applications of Gauss's law. First application. Is to find the intensity of electric field near an infinitely long charged wire. Here is an infinitely long uniformly charged wire. Let its linear charge density be lambda. Charge per unit length is lambda. Our aim is to find intensity of electric field at this point P, which is at a distance r from this wire. We want to find the value of E here. You form an imaginary Gaussian surface in the shape of a cylinder. Of length L, radius R, with the wire lying on its axis. Now this Gaussian surface has got three surfaces. One is this curved surface. Let me take a small area ds here. ds1. Surface area ds1. Here I am taking a small surface area ds2. On this flat surface, these two are flat surfaces. This is a curved surface. Here I am taking another curved surface, small surface area ds3. You know, here the angle between electric field is always perpendicular to the wire. Angle between electric field and ds1 is 0, small area. Here the angle between electric field, at this point electric field from the wire will be in this direction, E. What will that be? 90-degree angle between these two. Here also electric field on this flat surface is going to be perpendicular to the area vector. Let me call this area E2, E3. This is E1, which is E, which we want to find. Now what is the total flux over this entire Gaussian surface, closed surface? Surface integral E dot ds. I can leave this E, let it be E only, general case. So its magnitude is not the same as that. This will be surface integral E ds1, that is over the entire curved surface, plus surface integral E ds2 plus surface integral E, what dot product is there? Huh? Dot ds3 now I'm erasing this figure. This is equal to, you know, the angle between E and ds1 was 0. Therefore, surface integral E ds1 cos 0. Here the angle was 90 degree. Surface integral E ds2 cos 90 plus surface integral E ds3 cos 90. We know that cos 90 is 0. Cos 90 is 0. Therefore, what do we have here? And cos 0 is 1. Surface integral E ds1 plus 0 plus 0. You know the value of E is same at all the points on the curved surface, because all the points on the curved surface are the same distance r from the wire, which is the axis. Therefore, this is going to be E surface integral ds1. What is surface integral ds1? Curved surface area of that cylinder. Cylinder was having radius r, length L. Therefore, you have E into 2 pi r L, because the curved surface area of that cylinder was 2 pi r L. So this is the total flux over the Gaussian surface. By Gauss's law, what should this be equal to? It should be equal to total charge enclosed upon, what did we, total charge enclosed upon epsilon naught. So what did we get here? 2 pi r L E. Okay. But by Gauss's law, what should phi be? It should be Q upon epsilon naught. What is the charge enclosed by this Gaussian surface? You know, it was a cylinder of length L. That means the charge enclosed in it is a wire of length, the charged wire of length L. Therefore, Q is equal to, what is the charge per unit length? Lambda into L. Therefore, what do we have? What is this phi? 2 pi r L E. And what is Q? Lambda into L. Lambda L upon epsilon naught. Our aim is to get an expression for E. So what will get cancelled here? L and L get cancelled. And what will be our E equal to? E will be equal to lambda upon 2 pi epsilon naught r. This is the expression for intensity of electric field near an infinite long uniformly charged wire. Okay. You can put in the vector form this into r cap.